The final frontier beckons, a new space race begins. Space has always captivated humanity. Now it's bustling with activity. Launch numbers are soaring. We are witnessing a new era of space exploration. SpaceX stands out as a major player. Their reusable rockets are transforming the industry. Elon Musk's company has made space more accessible. But amidst this excitement, a new contender emerges. SpinLaunch offers a radical alternative. Forget fiery rockets. They propose a different method: kinetic energy. Imagine a giant centrifuge flinging payloads into orbit. This audacious concept has sparked both intrigue and skepticism. Could this be the future of space travel? The allure of space travel lies in its potential. It promises scientific discovery and technological advancement, but the high cost of traditional launches has been a barrier. SpinLaunch aims to shatter this barrier. Their vision is to make space travel more affordable and sustainable, but can they overcome the immense technical challenges ahead? The journey will be fascinating to observe. SpinLaunch burst onto the scene with a bold proposition. They promise to revolutionize space access. Their approach is unconventional, to say the least. Imagine a massive circular accelerator. Inside, a payload is spun at incredible speeds. Then it's released, launched skyward by pure centrifugal force. This is the essence of SpinLaunch's vision. The company was founded by Jonathan Yaney in 2014. His goal was to create a more sustainable and cost-effective launch system. Traditional rockets rely on chemical propulsion. They consume vast amounts of fuel and produce significant pollution. SpinLaunch seeks to eliminate these drawbacks. Their system is powered by electricity, making it cleaner and more efficient. However, this radical approach comes with its own set of complexities. The forces involved in such a launch are immense. The payload must withstand extreme g-forces during acceleration. The technology is still in its early stages. SpinLaunch has conducted several suborbital test flights, but achieving orbit with this method remains a significant hurdle. Despite the challenges, SpinLaunch has garnered attention. Investors see the potential in their disruptive technology. The company has secured significant funding to continue its development. Whether SpinLaunch succeeds in its ambitious goal remains to be seen. But their innovative approach has undoubtedly shaken up the space industry. The physics of a giant whirligig, how SpinLaunch aims to defy gravity. At the heart of SpinLaunch's operation is a fundamental principle of physics: centrifugal force. Imagine a ball on a string, swung in a circle. The faster you spin it, the stronger the outward force. This force is what keeps the ball moving in a circular path. SpinLaunch applies this same principle, but on a much grander scale. Their system consists of a large, vacuum-sealed centrifuge. Inside, a launch vehicle carrying a payload is attached to a rotating arm. This arm spins at incredibly high speeds, building up tremendous centrifugal force. At the precise moment, the vehicle is released. It's flung upwards with enough velocity to reach the upper atmosphere. This kinetic launch method offers several theoretical advantages over traditional rockets. First, it significantly reduces the amount of fuel needed. This makes launches cheaper and less polluting. Second, it eliminates the need for complex and expensive rocket engines. This simplifies the launch system and potentially increases reliability. Furthermore, the SpinLaunch system is designed to be reusable. After each launch, the launch vehicle can be recovered and refurbished. This further reduces the cost per launch. The centrifuge itself is also reusable, making it a sustainable solution for frequent launches. However, translating this seemingly simple physics into a functional launch system is a monumental engineering challenge. The forces involved are immense, and the technology must operate flawlessly to ensure a successful launch. SpinLaunch faces an uphill battle in proving the viability of its system. Battling g-forces and material limits. The hurdles on SpinLaunch's runway. While SpinLaunch's concept is intriguing, the practical challenges are immense. One of the biggest hurdles is the extreme g-forces experienced during acceleration. The payload is subjected to forces many times stronger than gravity. This puts immense stress on the structure and components. Designing a launch vehicle that can withstand these forces is a formidable task. It requires advanced materials and construction techniques. The payload itself must also be able to tolerate the g-forces. This limits the types of payloads that can be launched using this method. Another challenge is achieving the precise velocity and trajectory for orbital insertion. The launch vehicle must be released at the exact moment and with the correct speed and direction. Any deviation could result in the payload failing to reach orbit or even being destroyed during re-entry. The SpinLaunch system also relies on a near-perfect vacuum inside the centrifuge. Any air resistance would create drag and reduce the launch vehicle's speed. Maintaining this vacuum in a structure of that size is a significant engineering feat. Furthermore, the environmental impact of sonic booms generated during launch needs to be addressed. The high-speed launch vehicle creates shockwaves as it breaks the sound barrier. These shockwaves can be powerful enough to cause damage on the ground. SpinLaunch must find ways to mitigate these sonic booms. This might involve launching from remote locations or developing technologies to suppress the shockwaves. A niche in the cosmos, where SpinLaunch might find its footing. While SpinLaunch may face an uphill battle in competing with traditional rockets for general-purpose launches, there are niches where its technology could prove advantageous. One such niche is the launch of small satellites, particularly CubeSats. These miniature satellites are becoming increasingly popular for various applications. The lower cost and higher launch cadence offered by SpinLaunch could be particularly attractive for CubeSat operators. Currently, CubeSats often have to piggyback on larger launches, leading to delays and limited schedule flexibility. SpinLaunch could provide a dedicated launch service tailored to their needs. Another potential application is launching raw materials from the moon or asteroids. The lower gravity of these celestial bodies would make it easier for SpinLaunch to achieve escape velocity. This could pave the way for space-based manufacturing and resource utilization. Imagine a future where SpinLaunch systems are deployed on the moon. They could launch lunar regolith into orbit for use in construction or as propellant for spacecraft. This could significantly reduce the cost of establishing a permanent human presence in space. Furthermore, SpinLaunch's technology could be adapted for atmospheric launches on Earth. The system could be used to launch research payloads or even deliver cargo to remote locations. While not reaching orbit, these suborbital flights could still provide valuable data and services. SpinLaunch's success will depend on its ability to overcome the technical challenges and find its niche in the evolving space industry. Adaptability and a willingness to explore unconventional applications will be key to their long-term viability.